All right, so we're going to be looking at the principle of superposition. And after we look at the principle of superposition, we'll look a little bit at electromagnetic waves. All right, so my hope is to be able to kind of highlight some things that you read in your reading or maybe you missed, but things that are probably going to be important to you as we proceed. Okay, so first is the principle of superposition. All right, now the first thing that I want to point out is this whole definition. These are all important pieces. When two or more waves of the same nature meet or interfere, the resultant displacement is the vector sum of their individual displacements. And we're going to talk about this in detail a little bit more, but I want you to recognize kind of what's going on here. Okay, so the important piece is that we need to have two or more waves meeting and interfering. So they have to be running into each other. They have to be localized in the same position at the same time. That's where the superposition occurs. Just having two waves doesn't mean you have superposition. They actually have to be in the same place trying to affect the same medium at the same time. Okay? The two waves also have to be the same nature, right? You can't have a light wave and a sound wave cause superposition. They're not going to interfere with each other. They're different types of waves. They affect different things, right? And so they do have to be the same nature, working with the same medium and causing the same types of changes. Okay? Now, the resultant displacement is the vector sum of individual displacements. So when we look at a wave, we usually have a wave that is something like this, right? And you've got kind of an equilibrium point here, right? And so when we talk about displacement, we're talking about how far is that point on the wave from the equilibrium, right? So when we talk about displacement, anything up will be positive, or sometimes if we're working to the right would be positive. Anything down would be negative. That's why we're talking about a vector sum, because the positives and negatives are going to be important. You can't just add values together. You have to make sure that you have the appropriate positives and negatives, all right? So that's the idea of the principle of superposition. We're going to look at that in the upcoming slides just to make sure that we really have an idea of what's going on, all right? So here's the first question we're going to look at, just kind of get in make sure that we've got this idea down. We've got two wave pulses sent from a stretched out rope. So here's my rope. Okay, sorry, it's not very straight. I'm sending out two pulses. Pulse A is traveling towards the right with an amplitude of +2. So here's my pulse. It's got an amplitude of 2, and it's moving towards the right. Okay, the second, pulse B, is going to be over here. It has an amplitude of -4. Now, saying -4 actually with amplitude is not really correct. And that's why in the previous slide you can't use the word amplitude when you're talking about superposition, because you're not really adding amplitude. Amplitude on the blue one is 2. The amplitude here is 4, right? The negative is actually now talking about a displacement, that it's down, all right? This one is moving to the left. That's B. Now, when we put those two together, when these two run into, now right now no superposition is happening, but A is going to move down like this, right? It's going to keep moving, sliding down the rope. B is also going to move down, right? Depending on its speed, right? At some point, they're going to overlap. And it says the two pulses meet and completely overlap. So when they completely overlap, right, assuming that they're symmetrical, you've got a +2 for this one, and then you've got a down 4 for that one. So when you put those two together, the up 2 and the down 4 is going to result in a down 2. Those two, when you put them together, when we look at the string can't be in both these places at once, right? You had this string, and the wave was moving down the string. Here, this wave was moving down the string. The string can't be in both those locations at the same time. So what happens is superposition. They combine anywhere where you have overlap. They're going to combine, and at this point, the down 4 and the +2 are going to combine to give me a down 2. And so at some point in between, your string will look something like that. The answer to this question right here is, of course, D. All right? So that's to give you a basic idea. Recognize that we're talking about those vector displacements from the center, from equilibrium. All right? So there we go, letter D. Now, here's a little bit more in-depth example, all right? We've got waves moving at a rate of 1 unit per second. I've got two different pieces here, right? I've got this one right here, which is these two blocks down to the left. And then I've got this one over here, which has a little bit more complex wave. It looks like it's been shaken up and down. And these two pulses are moving towards each other. Because they're in the same medium, they're probably going to have the same speed, and in fact, it does say it's moving at 1 unit per second. All right, these two are going to run into each other. We're going to look at what happens as time progresses. All right, so here's our first second. You can see that the red one here has moved into the right one. It was in this position right here, and it's just moved over to the right 1 space, because that's what it says. It's moving to the right at a rate of 1 unit per second. Okay, the blue one, similar. See, it was 1, 2 spaces over from the right. Now it's 1, 2, 3 spaces over from the right. The rest of the shape has stayed the same, right? Now at this point, you'll see there's actually no overlap. They do meet here in the middle, but there's no overlap between the pulses. Okay, so the actual string here is just going to follow the shape of those, and that's what you're going to see right here, is when we put them together, we end up getting a shape like that. So that's after 1 second. Okay, we're going to move on to 2 seconds now. I'd like for us to see what happens when we put on the second. All right, so when we add on the second, and unfortunately, there we go. Oh, it's not going to let me. There we go. Okay, we're going to get rid of some of those drawings there. Okay, so I'm going to add on the second now. And you can see that the red one has moved another space over. It's right here, right? It was 1 space over. Now it's 2 spaces over. Now in the second, 2 seconds have passed now. It's now moved over to the right 1 more space, right? Same thing with the blue one. The blue one, which was 3 spaces over, is now 4 spaces, 1 more space to the left. So it's moved over. So now those individual waves will continue to exist the way that they do. However, the string itself, whatever this medium is, isn't going to look like that. The particles in the medium have to adjust because they can only be in one place at a time. It can't be both here and here at the same point in time. So what's going to happen is they're going to combine, right? You see here in the first square that we're going to combine this -1, that's 1 below the center, and this +2, which is 2 above the center. So when we put that together, which you'll see right here, you see that we end up with a +1. +2, -1, add together to give us +1. Now right here, we see that the red one is down 1, and the blue one is down 2. So if I put those together, I'm going to have a down 1 for the red and a down 2 for the blue, and I add those together, and I get, look over here on the right, I have a down 1, 2, 3, just like that. All right? And so that's the idea of superposition, is that the overlap, the places where they overlap, we're going to add together those displacements, okay? Add together those displacements so that we can see what the new shape of the string looks like. The red and the blue we won't see. They're still there. They continue moving, and we're going to see what happens in the next step. However, this is what the black is what the string or the medium will look like at that point in time, okay? So we'll go ahead and move those up, just so that we'll be able to compare. And here's the next second. Okay, you'll see the red one has moved just over to the right a little bit more. It goes right here. It's overlapping the blue. So it's moved over to the right 1 more space. The blue one has moved 1 more over to the left. And you can see how everything continues to move. The red and the blue don't interact with each other other than that idea of superposition. They don't ruin each other. They don't cancel each other out. They still exist. It's just for that instant they are superimposing. All right. Now, in this situation, you can see that there is no overlap. There's this place where the lines are overlapping, but that's really not going to be important. The string isn't going to go there and come back in all in that instant. So when we put this together, it's just going to look like this. The blue won't need to be there anymore, just like that. And so we'll end up with a string that follows the blue, and then it follows the red, and then that's what it'll look like. Okay, so that's the first 3 seconds. Now, if I put all this together, if I take out all the red and blue, you can see first second, it's moved over, second, third second, and this is what the string looks like. If we continued on for another second, you would see the blue one is all by itself over on the left, and the red one all by itself over on the right, and those waves, those pulses, the energy continues to exist. Okay, and that's the important idea here, is that when we're superimposing, we're not adding or subtracting or destroying anything. Both continue to be there. It's just in that instant we have to have a way of combining those two ideas together. All right, so I wanted to show you this. Okay, this I think is an important idea. This is a transverse wave. Okay, if you watch, you should be able to see this wave, right? I'm showing the top of the wave right there. See how it's moving to the right? The wave is definitely moving to the right, or you can watch a trough. You can see what's happening. Okay, but now I want you to look at an individual molecule. Okay, so maybe choose one of these guys here in the middle, like this one right here. Okay, look at him. He's just going straight up and down. Okay, that's what a transverse wave is. A transverse wave is when the energy of the wave, or sometimes energy, I promise I can spell, not that it really matters, but energy is moving one way, and then the medium, the particles in the medium are moving perpendicular to that energy. That is a transverse wave. Okay, so when we talk about transverse waves, that's what we're talking about. Now, this cannot happen a fluid. Now, fluids are liquid or gas. Okay, because the bonds between the molecules are not strong enough in a liquid or a gas to actually do this. See, what happens is, as one particle moves up, it's grabbing the particle next to it and pulling it up after, which pulls the next one up. And so that's where you get this wave, and then as it starts to come down, then it starts to pull those down as well, right? And so it pulls the particles next to it. That can't happen in a fluid, in a liquid or a gas. Now, some liquids like water is almost kind of an exception because there's some hydrogen bonding going on there. There is some connection between the molecules, and they can actually do a little bit of pulling up and down. Most of the time, we're going to say that this does not happen in a fluid, okay? But it is a most of the time, all right, which we'll look at in just a second. Okay, so that's the idea of a transverse wave. The medium, or the particles in the median, are moving perpendicular to the direction of the energy transfer. Okay, so transfer energy is perpendicular to the particle motion. One thing to recognize is that the medium itself, the thing that the wave is traveling in, whether this is air or a liquid or a solid or whatever else, that medium isn't moving, right? I mean, the particles, yes, are moving up and down, but it's moving up and down around an equilibrium. The mass itself is going to stay right here, right? The energy, yes, is moving that way, but the mass that was in this black box in the beginning is still going to be in that black box, right? It's not, this black box is not moving over to the right with the wave, with the energy. And that's a really, really important idea as we progress. Okay, now this is an example of a sound wave. Okay, now sound wave is longitudinal. It has to be longitudinal because it's in air, right? Or in liquid, right? Unless we're talking about something that's solid. But in air, it has to be a longitudinal wave because the particles aren't connected, right? The air particles are far enough apart. We've talked about ideal gases and minimum time of interaction. They're far enough apart that moving it up and down isn't going to make anything next to it move. Now, it might run into something else and cause that to move in the same direction, but that's why longitudinal means that we have parallel motion, right? The wave, or the energy, will move parallel to the particles. Now watch. You can see right here, here's one wave. See how that, oh, sorry, I'm going a little too fast. See how that wave, I'm staying right above that mass, right, is moving over to the right. You can see that the waves, by looking at the picture, when you look at the big idea, it is the wave, the energy in that wave is moving to the right. However, again, recognize that single point. Look at this guy right here. What is he doing? He's just moving right and left. Right? So he's moving right and left. The energy is moving to the right, and so they are moving parallel. The difference, again, is that the wave does actually travel. The energy is propagated. We use the word propagated because it's taken from one point to another and it's transferred from one particle to the next. The energy is moving to the right. However, the particles as a whole are not moving just kind of in general, right? Okay, let's go on to the next one.